In this video, we are going to take a detailed look at this limit here written in white, namely that the limit as x approaches 0 of sine of x divided by x equals 1. This is a limit that calculus students use all the time to help them solve limit problems. So if you look over here on yellow, we find that in this format, the sine of 2x divided by 2x does indeed equal 1. However, here in orange, this limit, sine of 2x divided by 2x, does not equal 1. So in this video, I'm going to talk about when you can trust this. When do you have the sign of stuff, the sign of the argument divided by the argument? When can you trust it that it equals 1, and when is it that you cannot trust it? Folks, we are also going to investigate this second classic limit shown here in white, that the limit as x approaches infinity of the sine of x divided by x equals 0. And we're going to look at whether that holds true when you have here the sine of 2x divided by 2x. Again, the argument is matching the denominator. Does this limit equal 0? How about here in orange? The argument of the trigonometric function matches the denominator. Can we trust this to be equal to 0? In summary, we're going to look at when we can trust the fact that you have the argument of the trigonometric function matching the denominator. When can we just jump to this value of 0? Let's look at this first limit in yellow and determine if this limit, where you have the sign of the argument with the same argument in the denominator, will yield the same result as this classic limit when you have the sign of the argument with the argument in the denominator equal to 1. Okay, so to do this, I've rewritten the classic argument using theta, because as you'll see, the key to determining whether or not this classic limit is going to hold is by using substitution. So the first thing we're going to do is try to recreate this classic limit. So we're going to have theta equal to 2x. Okay, let's do that substitution. So this gives us now the limit as x approaches 0 of the sine of theta over theta. Okay, all I did was take theta and substitute it in for 2x. Okay, but we have a problem here. We have a limit with x going to 0, but yet we have theta inside the limit. So we have to rewrite this in terms of theta. So the way we do this is we ask ourselves, okay, we know we have to write this limit as theta goes to something. All right, let's rewrite this part here. So the question is, as x approaches 0, what does theta approach? So let's do that. Let's take this substitution that we did right here, and as x approaches 0, what happens? Theta approaches 2 times 0, which equals 0. So we see that this does not change. Okay, so this stays. Theta approaches 0, sine of theta over theta. This matches our classic limit, therefore it holds. Next, we are given this limit in yellow, where we have the limit as x approaches 0 of the sine of 2 divided by x with the entire numerator divided by 2 over x. So in summary, we have the argument matching the denominator, and the question is, does this classic limit hold true? Will we get 1 when we evaluate this limit? So we're going to do something similar. We're going to let theta equal 2 over x, and we're going to substitute everywhere we see 2 over x, we're going to replace that with theta. So that's going to give us sine of theta over theta, because we're trying to match this classic limit. But folks, we have a problem here. You can't have x going to 0 when you have thetas in the limit. So we have to rewrite this limit and determine what is theta doing as x goes to 0. All right, so let's do a little problem over here. As x goes to 0, okay, we have theta 2 over a very, very small number, say 2 over 1/1000th, right? It's approaching 0. It's getting smaller and smaller and smaller. If you do keep change flip here, you're going to see that theta is going towards positive infinity. And if you want to look at what happens if x is approaching 0 from the left, then you're going to have 2 over a very, very small negative number. Let's call it negative 1/1000th, right? As you approach 0 from the left, here you're at negative 0.1, negative 1 over 10. Now you're at negative 1 over 100, negative 1 over 1,000,000. This blows up to negative infinity. So folks, we're either going to get that theta is going to positive infinity or theta is going to negative infinity. But in both cases, we will find that this limit equals 0. Okay, because we recognize that as theta approaches positive infinity, sine of theta over theta, that's classic limit number 2, and that equals 0. So we could see this does not hold. And the reason is this changed. Originally x was going to 0, but now theta is going to infinity or negative infinity. And in both cases, you're going to get 0. So it does not hold. Look, x is in the denominator in the argument. This does not hold. You can't jump to this. You can't say that the sine of stuff divided by the same stuff always equals 1. Now, let's quickly, we know that the limit as theta approaches positive infinity equals 0, because that's classic limit number 2. But let's just quickly look at whether or not that the limit as theta approaches negative infinity does in fact also equal 0. Alright, so here's our limit here. And to do this, we're going to use the squeeze theorem. Alright, so we're going to put sine of theta here. And we know that no matter what the value of theta is, the y value is going to fluctuate between 1 and negative 1. Then what we're going to do is we're going to divide this entire inequality by theta. Okay, so now these limits match. And now we're going to plug in negative infinity here, because that's what we're trying to figure out the limit of. So you're going to have negative 1 over negative infinity. That's going to go to 0. Less than or equal the limit we're trying to find. And 1 divided by negative infinity, that's also going to go to 0. So we see that whether the limit is heading towards negative infinity or positive infinity, this is going to go to 0, and these are not going to match. In this next limit, we are asked, what is the limit as x approaches 0 of the sine of x plus 1 divided by x plus 1? The sine of this argument with that same argument in the denominator, does that yield 1, just like this classic limit to the right? So let's go ahead and do what we've been doing. We're going to let theta equal the argument. We're going to rewrite this. We're going to replace x plus 1 with theta. We're going to end up with sine of theta over theta. The problem is we have x going to 0, but we have thetas in the limit. So we have to rewrite this with theta going to something as x approaches 0. So if we look here into our substitution, we see that theta equals x plus 1. So as x goes to 0, theta is going to go to 1. So let's add that here. So now, if we plug in 1 here, we're going to have the sine of 1 divided by 1. And if you plug that into a calculator, you're going to see that the sine of 1 equals this number here, 0.01745, and clearly this does not equal 1. So in this scenario, it does not hold. You can't identify the argument in the denominator and jump to the classic limit. Notice here, folks, originally x was going to 0, theta changes and goes to 1. Incidentally, this 1 here is in degree mode. If you wanted to change that to radians, which is what we usually use in calculus, let's see where that takes us. So we have 1 degree, and we want to know how many radians that is. So let's multiply by the conversion factor that we have pi radians for every 180 degrees. So if you put in the sine of, here the degrees cancel out and you get radians. If you put in the sine of pi over 180 when you do radians mode on your calculator, you're going to get the same value. Let's next investigate classic limit number 2, where we have the limit as x approaches infinity, sine of x plus 1 divided by x plus 1. So the argument matches the denominator. This is the classic limit. Does this equal 0? Let's let theta equal x plus 1. Let's rewrite this limit as x approaches infinity, sine of theta divided by theta. This x going to infinity, we can't work with the x, we have to change that to theta. So we're going to rewrite the limit as theta goes to what of sine theta over theta. Let's look at our substitution box here, and we ask ourselves, as x goes to infinity, theta is going to go towards infinity plus 1, otherwise known as infinity. So let's change that. So now we have the classic limit is intact. The limit as theta goes to infinity of sine theta over theta is equal to 0, and indeed we have a match. So folks, what did we learn based on the last two examples? If you have this function right here, you're trying to take the limit as x approaches 0. It turns out the classic limit does not hold. Recall, we got the result here, 0.01745. However, if you look at classic limit number 2, same setup, same argument, same denominator, it does hold. This doesn't hold, this one does. Folks, I want to spend a few moments on the derivation of classic limit number 1. And let's see if the squeeze theorem works. We know that the sine of theta, the y value is always going to lie between 1 and -1. So if we try to recreate the limit in the center and divide through by theta, we're going to have what's shown here. At this point, when we do the squeeze theorem, we apply the limit here and here. And that limit has to be the same in order to apply the squeeze theorem. But the problem is, if we look at the graph of y equals 1 over x, you could see as you approach 0, either from the left or the right, the limit is not going to exist. In one situation, you're going to head towards positive infinity, and in one towards negative infinity. And if you do y equals 1, -1 over x, you're going to get a similar situation here. It's just going to flip like so. And again, the limit as x approaches 0 doesn't exist. So you cannot use the squeeze theorem here. So where does the derivation come from? You could do L'Hopital's rule here, because if you just plug in, you're going to have a 0 over 0 situation. And if you take the derivative of the top, you're going to have cosine of theta. Derivative of the bottom, you're going to have 1. So we're using L'Hopital's rule here. And now if you apply the limit, if you plug in 0, the cosine of 0 is 1. But I've read somewhere that this is circular reasoning. I don't really understand that. So let's spend a few moments on what is the derivation of this classic limit. Okay, so next we're going to endeavor to prove this classic limit number 1. Limit as theta goes to 0, sine of theta over theta equals 1. Now folks, we know that in the unit circle, if we pick a spot on the unit circle, the x coordinate here is going to be the cosine of that angle, and the y coordinate is going to be the sine of that angle. So we know this distance right here, which represents the y coordinate, is the sine of theta. But the other thing to point out in this derivation is that this distance here along this circle, distance of that portion of the circle is the same as theta in radians. So look, if we look at going from 0 to 2 pi, our theta would equal 2 pi radians. Well, folks, what's the distance if you go all the way around? Well, we know this is pi radians, and we know that's 2 pi radians. So we have the circumference, which is 2 pi radians in green, matching the angle, which is 2 pi radians. Here's another example. If our angle theta is pi, the distance here is pi radians. Or if theta equals pi over 2, the distance around that circle is pi over 2. These match on the unit circle. And we're going to use that fact that this distance, this arc length, matches the theta. We're going to use that to prove classic limit number 1. Okay, like we just spoke about, this dotted line is this distance represents sine of theta. That's here in the numerator of our limit. And we know that this arc length represents theta, which is in the denominator of our classic limit. Now, folks, look what happens as theta goes to 0. As theta goes to 0, that means this green line, theta is going to 0, you have this scenario. Okay, so that's angle theta. It's getting smaller and smaller, approaching 0. Now, folks, look at our lengths. Here's the length of sine of theta here. That's in our numerator. And look at the length of the arc. That's theta. That's in our denominator. And if you go even further, if you take down to here, look what happens to these distances. That distance, sine of theta, right there, and that distance right there, let me do that in yellow, that distance, this distance here, which is the arc length, that's the denominator. Here, let me write it over here. Sine of theta over theta. Sine of theta is right there in green. Theta is in yellow. They are approaching the same exact distance. That means this fraction goes to 1.